Welcome to solverfy.
Okay, in this problem we have 40 eV electrons in a beam passing through a single slit with a slit width and traveling a distance x to a screen where there's an interference pattern created. We are first asked to find the wavelength of these electrons, then the time of flight, delta t, it takes for electrons to travel from the slit to the screen. We're then asked to find the uncertainty in the y momentum, and finally the uncertainty in y position. Okay, so the equations we'll need is the definition of a de Broglie wavelength, h over the momentum. We will need the single slit interference equation. And we can also use this useful trigonometric result found earlier in the chapter for single slit interference, which relates the ratio in y and x momentum to an angle, the tangent of an angle rather. And finally, we can use the Heisenberg uncertainty principle, which relates the product of uncertainties in y and p to a constant, reduced h, also known as h bar. Here are the constants we'll need. We'll need the mass of the electron and h and h bar. So let's jump into it. So to start, we can take the definition of a de Broglie wavelength, h over p, and using the fact that p is mv and k is 1/2 mv squared, can combine these two results into k equals p squared over 2m. Thus, p is root 2mk. Plugging this into the de Broglie wavelength formula, we can get a numerical result. Lambda equals 1.94 times 10 to the negative 10 meters. Okay. So for part B, we're asked for a time of flight. To get it, we can simply take the distance from slit to screen, divided by the velocity. And once again, we can use the kinetic energy to isolate velocity in terms of k. So this will come out to be x times root m over 2e, or 2k, rather. Numerically, we will have a time of flight of about 6.7 times 10 to the negative 7 seconds. Now, if we know the x velocity, which you can get from kinetic energy, we actually used it. It's root 2k over m, which is equal to about 3.75 E6 meters per second. If we know this, and we know the mass, we know momentum. So px, simply mvx, which we have. We then can relate this to the y momentum by noting, oh, actually, let's take a step back. Before we do this, we need to find the angle to the first minimum. We can do this by using the single slit interference equation. A sine theta is equal to n lambda, set n equal to 1 for the first minimum. We know lambda, we know a. We can then find theta by taking an arc sine, lambda over a, which gives us a very small angle, 0.002 degrees. Okay, so because theta is going to be very small, we can say that this ratio, py over px, which is usually equal to tan theta, we can do a small angle approximation to say that it's simply equal to theta. Thus, py is simply equal to px theta. comes out to be 1.3 times 10 to the negative 28 kilograms meters per second. Okay. For this last part, it's also worth noting that this is our delta Py. And this formula is motivated in the text. I'm simply using it. For this last part, we use Heisenberg's uncertainty principle. Delta y, delta Py greater than equal to h bar. Thus, delta y is simply h bar over delta Py. Okay, which will come out to be 3.9, or rather, I should say, it comes out to be about 8 times 10 to the negative 7 meters. How does this compare to the slit? This is slightly larger than the slit. Actually, nope, slightly smaller than this. It's quite smaller than the slit. The slit width, recall, was 5 micrometers. This is a lot smaller than that. Just making note. So this is actually not, this uncertainty isn't very bad. Okay, so those are the main results. We found lambda, we found the time of flight, and we found uncertainties in momentum and location in the y direction on the screen. And that's it. Thank you very much.